Hi, it's Miss Adams from Flamingo Math. We're going to look at lesson 6 today. We should complete the lesson in one day. This lesson is all about predicting the end behavior of a polynomial function. If we know the degree of the polynomial, we can use the leading term to determine what happens at the extreme values. Since the power of the leading term is the highest degree, that term is going to grow at a rate which is significantly faster than any of the other terms as x gets very large or very small. Now, what do we mean by that? If we have y equals x to the second, we know that's a parabola going up. If that parabola was y equals x to the second minus 18x plus 95, this term is going to grow faster than the other two terms in that expression. That means the end behavior of the polynomial will correspond to the end behavior of that leading coefficient. In this case, the parabola has unbounded behavior on both sides up. To save us time, I've already written out the translations of these statements in this next example, understanding the language and the behavior. So phrase 1 says the inputs increase without bound. X is the inputs, and when I see that expression, x increases to infinity, that's the words increases without bound. You can translate that to say the x values are moving toward positive infinity. Just like in phrase 2, the inputs decrease without bound, or x is approaching negative infinity. X is approaching negative infinity, translates to the x values are moving toward negative infinity. And if we go to the y values, the output values increase without bound. That just means y is approaching infinity, or the y values are moving toward positive infinity. The y values are getting larger and larger without bound. And finally, phrase 4, the outputs decrease without bound means y is approaching negative infinity, or translating that, the y values are moving toward negative infinity. So using the language properly is important in our course. So let's consider this end behavior from a graphic point of view, being able to describe that. Can you translate and create a picture in your mind of what's happening and use the coordinate plane to answer the questions? So in first example, if the inputs increase without bound, what direction on the coordinate plane would we move? The inputs are the x values, so the x values increase without bound, we should be moving right. If the inputs decrease without bound, the direction would be moving to the left. So these are the x values. These outputs for number 3 and 4 are the y values. So if we have outputs increasing without bound, we would be moving upward. And if the outputs decrease without bound, we would be moving in a downward fashion. I'm thinking about a cubic function in that case. X is moving to infinity, and so is y. The end behavior is unbounded in an upward direction. And over here, the x inputs are moving downward, and the y values are also going in a downward fashion, or decreasing without bound. Can you figure out the missing pieces in these statements? The end behavior of a function describes what the y values of a function are doing as the x values increase or decrease without bound. The left end behavior of a function describes what the output values of the function are doing as the input values decrease without bound. So as we move to the left on x, decrease without bound. Visually, this would mean This would be the limit of the graph. So this is a calculus term, finding limits. And the right-end behavior of a function describes what the output values of the function are doing as the input values increase without bound. Visually, that would be the limit of the graph. So we're going to find out the limit is a y value. So what could we say here? The graph represents the function g, and we're going to use the graph to answer the question. As the input values increase without bound, what are the output values doing? So let's think about. As we move to the right, what happens to the y values? They're going up. They're increasing without bound. So here you would say they are increasing without bound. And as the input values decrease, so as we move to the left, what are the output values doing? The further left we go, the further negative. So these values are decreasing without bound. That's what we would say related to the statements to translate them verbally. So here's several ways we can mathematically shorten the phrase. As the inputs increase or decrease without bound, the outputs increase or decrease without bound. Let's take a look at those symbolic representations. Here you're going to want to become very familiar with this because these will be things you will see on the AP exam, and we'll use this limit notation in our course throughout the year. So as x approaches infinity, either positive or negative, the y values are going to approach positive infinity or negative infinity. That's symbolically. We've already practiced the verbal. And the limit notation, which is new to our course, you might want to put a little star by this. This is important to understand how to write it and how to read. We say the limit as x approaches infinity on our function f is at positive infinity, or you could replace that with negative infinity. And the limit as x approaches negative infinity is either positive or negative infinity. Let's look at describing end behavior now. So we're going to use the graph and fill in the following sentences, and then translate those sentences by using this new limit notation that we've just learned. So the left end behavior, using that graph, the left end behavior, as x approaches to the left is over here, as x approaches negative infinity, the y values are approaching negative infinity. The limit notation would be the limit as x approaches negative infinity on our function name, which is g of x, is also approaching negative infinity. In the right behavior, as we move to the right, the y values move up. So as x goes right, the y values go up. In limit notation, the limit as x approaches positive infinity on our graph g of x is approaching positive infinity. Our leading coefficient test tells us that power functions eventually rise or fall without bound as x moves toward infinity, whether that's left in negative infinity or right positive infinity. This behavior can be determined by the degree and whether it's even or odd degree, the main leading coefficient, and by the leading coefficient. So we're going to focus on the leading coefficient and whether that power, because when we say it's a power function, we mean the power is an even number or an odd number. I can't spell and write, coefficient. Okay, so let's give this a try. If our coefficient sign would have to be positive here. They're telling us positive and the power is odd. So what happens As we move to the right, the limit at the right, the graph is unbounded up, but the limit at the left, the graph is unbounded down. We have a positive leading coefficient and an odd power. Here you have a negative leading coefficient. And as you move to the right, the graph is unbounded downward, so the y values head toward negative infinity. But as you move to the left, the y values are unbounded upward. So this would be something along the lines of negative x cubed with other stuff. And this would be something along the lines of positive x cubed and other terms. On the third graph down, on the left here, we have a positive leading coefficient. Both graphs are going up on the left and up on the right. So positive and an even power, like x to the fourth. We're unbounded up on both directions as x moves right or as x moves left. And here we have a negative leading coefficient and an even power, something like negative x to the fourth. And our graph moves left, the y's go down. As x moves right, the y's go down. Our a value is negative. So we want to summarize that. The top row of graphs had odd degree, and the bottom row of graphs had an even degree. Describe the patterns you notice that help you identify those end behaviors. So you could put something down in your own words. What happens on the odd degree, that behavior, what happens? We have opposite directions. And then what happens if you have an even degree as your leading term, the behavior that you notice is the same directions. So you might be familiar with this from a previous course, Algebra 1 or Algebra 2. On this slide, we're just summarizing what we learned. Consider the domain and range for each degree family. As x moves right and x moves left, what do you notice about the y values on the graph? Well, we noticed on the even powers, the end behavior stayed the same, and on the odd powers, the end behavior was opposite directions. And how does the value of the leading coefficient A value affect the value as x moves right or as x moves left? And we notice that if the A value was a negative leading coefficient, then the end behavior directions changed. Instead of going down to up, it went up to down if it was odd. Instead of going up and up on an even, the A value meant down to down on the Y values. So here we want to use our calculator and sketch the curve with your calculator and then translate that over to the graph that we have. What do we notice about the function? Well, our n value is 3, so it's odd, and the A value is negative since it's -1. So we got that from this term here. And then answering the question, what do we know as the limit or as the x value approaches negative infinity? So we're moving left on x. The y values are going up. So as we move left, the y values go up. And up translates to positive infinity. And likewise, as the limit or as x moves right, the y values are down. And down is negative infinity. And how many turning points do we have? Well, the function is cubic, so we should have 3 minus 1, or 2 turning points. So example 1b, I would ask you to turn off your video and give this one a try on your own, and then come back to see if your answers match my answers. My graph looked something like this, and you can compare your answers to my answers. We see down at the bottom of summary, the graph of f has at most n minus 1 turning points, and the graph changes from increasing to decreasing, and the function has at most n real zeros. Now, what that means to us in relation to n, in this example, n was 4, so we had n real roots. We had 1, 2, 3, 4 zeros. And we had n minus 1, so 4 minus 1 turns, 3 turns. There was a turn here, a turn here, and a turn down here. So example 2, this is a good way to justify or explain what you know. For some polynomial g of x, if the limit as x approaches negative infinity on the graph is heading to positive infinity, and the graph has an odd number of turning points, what can you conclude about the leading coefficient of the degree of g of x? Can you justify your answer? So I'm going to ask you to write something in your own words that would help you grasp that concept. I said it something like this: if g of x has an odd number of turning points, which they told us here, the degree has to be even, and the leading coefficient will be positive, because the end behavior will be the same. If x went to negative infinity and y went up, then on an even power, x has to go positive infinity, and the y's will also be up. Example 3, the polynomial has the following characteristics. As we move left on x, y's go down, and as we move right on x, the y's go up. Can you sketch a possible graph of this behavior? So as x goes left, y's go down. It's got to go that way. And as x goes right, y goes up. It's got to go that way. So something's got to happen in between here, right? Something along those lines. Example 4, we want to use mathematical language and justify some more. The function h of x is given by this 6th degree polynomial. So power is even and the leading coefficient is positive. Determine the end behavior as x increases without bound and as x decreases without bound. So we want to write down using limit notation so we can show we can use mathematical language. The limit as x approaches infinity, h of x has to go up to positive infinity. And the reason we know that is because the a value is 3, and that's positive, and the power is 6. N is 6. And the reason the limit as x approaches negative infinity is also going to go up, and we know that because the degree is 6. It's an even degree. N is 6. So the behavior is going to be the same on the left and the right. Example 5, write the following in limit notation. So we're going to translate this statement into a mathematical sentence. As x decreases without bound, so the limit as x approaches negative infinity, our function is named p of x, it is going to increase. So the y values are going to increase without bound. And then the last statement, we want to be able to use that rule of 4 and translate from verbal to mathematical or from mathematical to verbal. So what does this say? As x increases without bound, the output values of the function, what's the function name? T of x. What are they doing? They're decreasing without bound. And that, my friend, is the end of lesson 6.